In the last video, we had our important formula for trig, and that is if you have a cosine of omega t plus b sine of omega t, you can rewrite that as r times cosine omega t minus delta, where r is equal to the square root of a squared plus b squared, and theta is the argument of a plus ib. I'm putting it like that because often it's handy to write a plus ib in the complex plane just to see what it looks like. And this is actually the inverse tangent of b over a as a four-quadrant inverse. Good. And now this is really handy for doing things like rewrite or write cosine of the square root of 3t plus I sine, sorry, this isn't complex. Cosine of 3t plus 2 times the sine of the square root of 3t as r cosine omega t minus delta, so we can analyze this expression. Okay, solution. Well, the r is going to be, so did you notice what we're really doing is treating this like a number 1 plus 2i. So 1 plus 2i, the r is equal to the square root of 1 plus 4, which is square root of 5, right? And then for the angle, we're at 1.2, we're there, right? So therefore, we can just take the normal inverse tangent function. You should check to see if this is a nice triangle. Is this a nice triangle with a 1 and 2? No. Well, I guess we could just find the, what's this other side here? Square root of 5. Okay, so but the point is that the angle measure is not a known value. So we'll just go ahead and write it as r is equal to the square root of 5. Theta is the inverse tangent of 1/2, or sorry, 2. Let's see, can I put, sorry, I was just putting that in my calculator. 1.1 radians. Okay, so now we know that this expression, cosine of square root of 3 t plus I, or plus 2, I keep writing I, I'm too used to writing the Euler's formula, that's equal to the square root of 5 times the cosine of the omega is the square root of 3 t minus 1.1. Good. And now this is fairly straightforward, right? To analyze, the amplitude of this periodic function is the square root of 5. The period is 2 pi over the square root of 3, and the frequency is the square root of 3 over 2 pi. The circular frequency is the square root of 3, right? And the phase shift itself is actually 1.1 divided by the square root of 3, right? Very good. Excellent. All right, so this is kind of the idea of what we're doing with the trig. We're really not going much further than that. What I might mention is how would you graph something like e to the minus 2t times cosine of square root of 3t plus 2 sine times the square root of 3t. Well, the idea is you would rewrite it this way, but you have this negative exponential hanging out here. So then you have square root of 5 cosine square root of 3t minus 1.1. And so your function has been shifted forward. So you're going to have this shifted cosine, and then it's going to have an amplitude of square root of 5. And so this is the function without or before I take into account the exponential function. And so as soon as I take into account the exponential function, what's going to happen to my function overall? This exponential function is going to squeeze the function together, right? And so the function is going to come down, and this, I can draw the exponential function as like an envelope over the top of this. And so the function might look like this now. right? And so the function, the oscillations start dying off. So the oscillations are going to 0. And so this is not a periodic function, right? We would call this, in our book calls this a pseudo periodic function. And that's because without the exponential function, right, we can extract the periodic part, and we could figure out what the amplitude and the period is for the pseudo periodic function. Good. Now, if this had been an e to the positive 2t, what would happen to my oscillations? Did you say that they were going to blow up? If you did, then you're right. So our exponential curve would look like that, and then your waveform would just start blowing up. Good. Maybe one other algebra issue that I might discuss when we're talking about this is how would you find the zeros of r cosine omega t minus delta? Well, the r doesn't matter, right? Because if you set this equal to 0, it really doesn't matter. So how do we solve for the t's in this problem? Well, think of it as taking the cosine of something equal to 0. And so if we graph the cosine function along the something axis there, we know that the normal cosine is periodic with period 2 pi. And so we know that the cosine function itself is 0 when we are at pi over 2, 3 pi over 2, 5 pi over 2. Oops, hang on. 7 pi over 2. It's pi over 2 plus 2 pi. Wait a minute. 5 pi over 2 is correct. I just had a moment there. I'm getting more and more senior moments. 7 pi over 2 and so on. Okay, it's an odd multiple of pi over 2. And so therefore, we could say that the fluffy cloud is an odd multiple of pi over 2. Uh-oh, one sec. I've got something ringing. Okay, so sorry for the interruption there. My phone just went off. That's pi over 2, plus or minus 3 pi over 2, and so on. And so now you can see, right, that the zeros of this function will be where omega t minus delta is equal to plus or minus pi over 2, plus or minus 3 pi over 2. We'll just do one more, 3, 5 pi over 2. It's the odd multiples of pi over 2. And so then you can add delta to everything. So it'd be plus or minus pi over 2 plus delta, plus or minus 3 pi over 2 plus delta, plus or minus 5 pi over 2 plus delta. And you might be saying, hey, what just happened there? Didn't we just shift our zeros forward by delta units? Didn't you tell me that the phase shift wasn't really delta? It was delta over omega? Ah, yes, we did. But see, we're not finished yet. We got to divide by... Okay, you probably didn't think that. Okay, we got to divide everything by our omega here, right? So we get plus or minus 1 over omega times pi over 2 plus delta. And so you can see that we just... the zeros shifted by delta over omega, right? But they also got scaled. 3 pi plus delta, and so on. Okay, so that's an easy way to get your zeros. That's not a plus there, that's a comma. Good. And so when we start to analyze the solutions to our differential equations, we're going to expect either periodic functions, or we're going to expect functions that oscillate but go to 0, or we can expect them to start small and oscillate and get bigger and bigger and bigger. Okay. Okay, I'll stop the trigonometry there, and then in the next video we're going to talk about solutions to the differential equations.